Hello! In this video we will be discussing how to build view and projection matrices for shadow mapping, specifically for use with a directional light. For the directional light, we will begin with the projection matrix. We must first decide if a perspective or an orthographic projection is the correct option. In the directional light case, an orthographic projection is usually the right choice, as all of our approximated rays of light are going to be parallel. If we used a perspective matrix instead, the shadows would change in size based on how large their depth is from the light's position. This would be weird for the directional light for many reasons, not least of which is that the directional light does not have a position. When building an orthographic matrix, we are basically defining the size of a box. We will need to determine width, height, near, and far clip values for this supposed box. A simple starting idea for defining our projection would be to build a box around our entire simulation world. The size of this box would then determine the width, height, near, and far values for our projection. Since everything in our world is contained inside the box, everything in our world would end up being rendered to our shadow map. Building the orthographic projection around our world will result in very low resolution shadows, unless your world is fairly small. This is because each texel of our shadow map can only have one depth value. If our shadow map resolution is fairly small and our world is large, this will result in each texel of our shadow map being used for a large portion of our world. We can improve this by increasing our shadow map size, but this will cost us both memory and speed. A larger shadow map texture will take up more memory, and it also determines the resolution that we render at. Higher resolution rendering costs more time. While we will certainly want to use a large shadow map size to increase the shadow map quality, we should try to improve elsewhere first. One thing we can do is to increase the quality instead of increasing the size of our shadow map resolution is to shrink the area that we are rendering to the shadow map. We will not need shadow information for areas of the world that are not currently in view. So instead of building our projection matrix around the entire world, we will build it around the currently viewable area. The view matrix for a directional light is where things are going to really get weird. The 3x3 orientation portion should be fairly straightforward. As mentioned in previous videos, we will use the light's direction to define our forward axis. Then we can use the last 4 steps of our look-at algorithm to build the right and up vectors. The weirder part, though, is going to be the translation, since our directional light does not have a defined position. A projection matrix just defines the size of the viewable area, not its translation. The translation is controlled by the view matrix. So, we will need to base the view matrix translation off of our camera's frustum. We would likely be tempted to position our light's view matrix at the center of our camera's frustum. Doing so will actually create the error shown in the diagram, as the location we are defining in our view matrix does not represent the center of our position, but instead the back of our projection. To fix this, we will move back from the camera's frustum center point in the negative light direction an amount equal to half the distance between our light's near and far clip values. That is the standard implementation for building the view and projection matrices for a directional light. In the next video, we will continue working on our directional light's view projection, focusing on one very common issue with this solution as discussed. This issue is typically called shimmering shadows.